Good morning. This is a presentation on active engagement in K12 engineering. This is my current field, my current area of research, and I would like to present some of my preliminary findings today. First of all, by way of introduction, my name is Astrid Northrup. I have bachelor's and master's degrees in petroleum engineering from Montana Tech in Butte. I also have a land surveying certificate from UW. I'm a registered professional engineer in Colorado and Wyoming, a faculty member at Northwest College in Powell, where I serve as division chair of physical sciences and associate professor of division of the engineering and science, the associate professor of engineering and math. I'm also a PhD student in science education at the University of Wyoming, and Dr. Andrea Burrows is my advisor. So the purpose of my study, when about 4 years ago I was on the committee impaneled by the Wyoming Department of Education to update the Wyoming K12 the Wyoming K12 science standards. Within the science standards are embedded engineering standards, and I was particularly interested in the way that these were presented. So from a brief literature review and from my own experience, I have found that most of the time when engineering is taught in K12, it's taught as purely hands-on or kinesthetic endeavor. And I think this leaves a lot out, and I think it leaves students not really understanding engineering or what engineering could mean in their own lives. So some of the considerations that I made in preparing this research is that while engineering includes technology, it's also an applied diversified science major, and that in order to study engineering, you need to first understand the physical laws that govern the way things work. Engineering is also a social contract because why we study what we study is often more important than what we actually study. The reasons behind what we do and the reasons behind certain areas of engineering are pursued while others are not. So society is impacted on all levels by engineering, and if students are brought into understanding this idea, I think it will make more sense to them and give more context to why engineering is an important field of study and an important career field. So as far as a career path, a lot of engineers do things other than build, and it's a common misconception or narrowing of focus that engineering is about building things, making bridges and structures and so forth, but there are a lot of other aspects of engineering: generating power, creating better materials, improving processes, cleaning up pollution, and that sort of thing that are not often thought of when it comes to thinking about engineering. So I really wanted to bring this idea of a broader context, both in terms of science and in terms of career path, as well as technology and math into engineering. So I've begun my literature review for this process, and the current state of literature on active engagement in K12 engineering indicates that it's largely focused on kinesthetic learning or hands-on learning, doing things in a classroom, but really not providing the context or the reasons why those issues are studied. So teaching engineering in context may be a gap in literature, and that is an area that I'm currently investigating. So in order to study engineering in context, I've constructed 4 modules, and I've deliberately shied away from construction or building. So the 4 modules I've developed focus on wind power, external combustion, water pollution, and polymers. But the way that I've developed these modules, I would like to provide them to interested K12 teachers because they can be used for any of the engineering standards. The basic layout and format of the module is transferable depending on what material or what standard a teacher is involved with at that particular time. So basically, I want to start with the foundation that math and science tells us how the physical universe works, and that engineers use all the tools available to them, math, science, and other things in the physical world, even common sense, to develop, improve, and optimize anything. So far in this process, I've presented these modules 4 times. First, I developed them for Dr. Burrows and presented them to pre-service teachers at UW. And since that time, I've presented them to Shepherd, Montana middle school students, Tennessee, Wyoming middle school students, Colstrip, Montana middle school students, and next week I will be presenting 2 of the modules to LCCC pre-service teachers. And the state of the project, I really didn't realize this was a research project when I began. I presented it as a practitioner, hands-on and in context, almost like a lesson plan, really. So developing it into a research project is sort of an interesting process, because I started with what to do, and then I worked backward to why we're doing it. So the literature review and the data collection are in progress. One thing I wanted to mention about the literature review is, due to issues of assent, I will not be collecting data from students. I'll only be collecting data from the chaperones and the teachers who accompany students, or any pre-service teachers that I present the modules to. So the module that I'm making an example of today is about polymers. And one of the reasons that I like to work with polymers is because it's an area of engineering that I think a lot of people are unfamiliar with. And the design of polymers in a classroom is very easy to do, very safe, and I think in my experience, kids love to do this. So we'll talk a little bit about the background of what polymers are, why they're important, what kind of engineers use polymers, and then I'll describe a method for making polymers of different properties in the classroom. So first of all, what is a polymer? A polymer is a substance that's bonded together at a molecular level. And there's some naturally occurring polymers such as silk, rubber, starch, DNA, and also some manufactured polymers such as Kevlar, which is body armor. Kevlar was invented in 1964. The lead chemical engineer on the process was Stephanie Kwolek, and she and her team developed body armor in order to save lives in law enforcement. Plastics, resins, paints, and polyurethanes are also polymers. So if you think about these substances, one of the things that may come to mind is they're sort of substances that don't feel like water. So water is what's referred to as a Newtonian fluid. Its behavior is described in certain mathematical ways. Polymers are broadly thought of as, or described as, non-Newtonian fluids, although there are many different types of non-Newtonian fluids to consider. So some of the polymers that we use every day: polyvinyl chloride, polyacrylamide, polystyrene, polycarbonate, polyethylene. So anything with a poly means many, polymer means many isomers, or many little pieces of molecules that are bonded together. So they tend to have very specific properties, and they can be engineered to have the properties that you need. I'd also like to point out that it's not the Coca-Cola in the bottles that is the polymer, it's the bottles that the Coke is in. So polymers are used in a lot of different applications. In farming, there's a substance called aquabond, and what aquabond is, it's a sugar polymer, so it's made out of sugar molecules, but it basically thickens the water. It makes the water more like a jello. And what that allows is, if a farmer doesn't have enough water, or if she has too much of a slope on a field that she is farming, the aquabond will make the water stay on the field longer, so that the crops and the soil can get the benefit of the water for a longer period of time instead of washing out of the field. And because it's made of sugar, it will just biodegrade and go away without any harm. Makeup, beauty, face makeup, fingernail polish are all polymers or have polymer characteristics. In oil recovery, fracking fluids and drilling fluids are polymers. And basically any time that a fluid is doing a job or designed for a specific purpose, it probably involves polymerization at some level. An example of this would be paint. When we want to paint a wall, when a person wants to paint a wall, you want the paint to remain liquid and flowable in the can. You want it to roll on very very easily without dripping, and then you want it to dry hard as nails and be protective to the surface that it covers. And at the same time, you also want to have it carry a very rich density of color and particular qualities, like whether the paint is a matte finish or a semi-gloss or a gloss. And all of those things have to be discovered and controlled at the engineered level. So when the can of paint comes to you, all of those things are already in place. And if it's good paint, it will work the way that you want it to for the job that you have in mind. So what is a polymer? Basically, if you take a bunch of, this is just a stylized version of chains of molecules, and you link them together, they cross-link so that there's more of, instead of just being in lines, there's more of an area. So what this does is it increases the stiffness, and there's less range of motion because the fluid behaves more cohesively. And crosslinkers work, and one of the best crosslinkers in the world is tetraborate, which we will also talk about in a few minutes. But basically, it just makes the chains bigger without changing the actual composition of the chemical composition of the material. So the way that you make a polymer is you have to have a cross-linking agent and a base agent, and some polymers that a lot of younger people are familiar with would be slime or oogalic or silly putty. And there's some activities for making silly putty using very common ingredients. The two main ingredients, the first one ingredient in homemade polymer is almost always borax. And borax can be bought in laundry detergent. It's called 20-multein borax, and it's very inexpensive and very readily available, and it's also very safe. There are two different ways that are common to make a polymer based on the borax crosslinker. You can use polyvinyl alcohol, which is usually available through like Home Science Direct, or you can use Elmer's glue. You stir them together and you start to notice some physical changes. Basically, the fluid will thicken and it will start to take on a different type of a consistency, and that's when polymerization is occurring. At that point, you can also suspend particles, like you can put frac beads or glitter in the polymer. You can also add food color to it to make it the color that you want. And depending on the relative amounts of borax and PVA or Elmer's glue that you use, you will get different stiffness or different rigidity of the fluids, and that property is referred to as viscosity. So you can test the process or the amount of viscosity by doing this. And it's also really easy at this point to separate out the idea of viscosity from density, because generally speaking, when something is very thick, we tend to think of it as being very heavy. But basically, the weight per volume, which is density of the fluid, remains unchanged. But what changes is the viscosity based on how much cross-linking has occurred. So this is just, when we talk about silly putty, we're really talking about using polyvinyl alcohol, which is a monomer, in taking the tetraborate anion, which is out of the 20-multein borax, and linking them together. So this sort of a chain links with this sort of a chain and makes this long chain, which is a polymer. And so what kind of engineers work with polymers? Chemical engineers in all of the applications we've just talked about. Agricultural engineers work with polymers in terms of aquabond, for example, petroleum engineers. If you've heard about hydraulic fracturing, hydraulic frac fluid is a polymer. It's generally based on bentonite, which is clay. It turns out Wyoming is famous for clay, for Wyoming bentonite. When you fracture a formation, you actually inject at high pressures this fluid with fracking beads, which is very round, well-sorted, sometimes manufactured sand, to keep the fractures that you create open and allow the oil to flow more readily toward the wellbore. Materials engineers are working with polymers every day, developing new and better types of plastics and all sorts of different compounds that improve our life, such as, if anybody, I don't know, it's a little beyond the scope of most children, but if a child has ever done any plumbing or watched their parents do plumbing, back in the old days when everything was made out of copper pipe and iron pipe, now things are made out of polyvinyl, what's called PEX. And PEX is like a million times easier to work with, lasts better, and if you have a flaw in PEX, you can just cut it out and put a new piece in. So PEX, in my opinion, is one example of how polymers have improved the quality of life. So to make, this is just a slide showing the ingredients. You can see it's very simple ingredients. We have 20-methyl borax and Elmer's glue or polyvinyl alcohol. Those are the three main ingredients. PVA either comes in an aqueous solution, or a powdered form. This jar is a jar of fracking beads, which you can suspend in the polymer as part of the experiment. And you can also use glow-in-the-dark glue if you want. You can use glitter, and then just some instruments here in order to measure cups and measuring spoons and so forth. I also always just keep wipes on hand and a kettle of warm water, because especially if you use powdered PVA, you want to be able to mix it up, and if you use warm water instead of cold water, it will dissolve much more quickly. So at this point, as I mentioned earlier, due to issues of assent, I'm only administering surveys to teachers and chaperones. I will not collect data from minors. So far I've collected about 30 surveys, and I'm in the process of qualitatively analyzing them. Specifically what I'm looking for is if the teachers and chaperones have changed their views of engineering based upon working with the modules. So for future studies, my hope is that more students and teachers will recognize how important engineering is and how accessible it is. How if you're interested in any field of study, engineering has a branch that will allow you to continue that field and also to improve life for everybody. So I'm kind of a fan of engineering, obviously, but right now in the United States, we're only educating about 1 engineer for every 4 engineering positions that come open, and it's a governmental mandate to try to increase the number of engineers that we are educating. So I believe if we start at the K12 level, work with the embedded engineering standards that are embedded within the science standards, that we will have a generation of kids coming out of K12 that will consider engineering as their college major. And in the end, I hope that this will expand people's views of what engineers do, and that when a person is asked, what is it that engineers do, they can answer everything. Thank you for your time.